Let's move on to 3 by 3 matrices to find the characteristic polynomial of. So you have a choice of how to find the determinant of 3 by 3s. Remember, we have the special 3 by 3 trick, or you can use cofactor expansion. So let's do one of each. So let's do this one with the cofactor expansion. So first off, I have to find what a minus lambda I is equal to. So that's 1 minus lambda, 0, negative 1, 2, 3 minus lambda, negative 1, 0, 6, and negative lambda. Okay. So I want to pick out a row or a column with zeros because I like zeros. So let's go for this last row, right? So I'm going to expand about this last row. So this is positive, negative, positive, 0, right? So the determinant, let me just label my work, what I'm doing, will equal, so I'll just say 0 times this, 0 times the determinant of the 2 by 2 that would be left over, positive, negative 6 times the determinant of the matrix that would be left over if I take out this row and this, or this row and this column, right? So let me make myself some room here. So I would have 1 minus lambda and 2, and a negative 1 and a negative 1. Sorry, make some room here. Okay, so that and that and that and that. Okay, so positive, negative, positive, negative, positive. So I keep the negative lambda, and I'm going to take the determinant of the 2 by 2 that's left over. All right, so this gives me negative 6 times, from the determinant here, I'll get 1 minus lambda times a negative 1, subtract a negative 2, so that gives me plus 2, minus lambda, these two multiplied, and subtract that. And there you go. So that's my characteristic polynomial. This would give me a cubic equation. I'm never going to ask you to find the cubic or solve the cubic equation. So this characteristic polynomial will what you'll be asked to find if you're going to get cubes, which you do in this case. All right, how about we do the 3 by 3 trick on this one? So let's first find out what a minus lambda I will be. So I'll have 4 minus lambda, 0, 0, 5, 3 minus lambda, 2, negative 2, 0, 2 minus lambda. Okay, so remember the trick. Now, let me make some room here. So the trick is going to be rewrite this column here and rewrite this column. Okay, so remember I'm going to do the upwards diagonals. So this times this times this. Oh, that's 0. This times this times this. Oh, that's 0. And the same here. So all the upward diagonals, which I was going to subtract, are all 0. Okay, so now let's go do the downward diagonals. So the downward diagonals would be these 3. So I'd have 4 minus lambda times 3 minus lambda times 2 minus lambda. And then these multiplied would give me 0. And these multiplied would give me the 0. So this is my characteristic polynomial. This one, I could actually set it equal to 0 and find the eigenvalues, right? Because it's nice and easy. So the eigenvalues are 4, 3, and 2. All right, let's finish off with a little bit of a proof here. So I want to show that A and A transpose have the same characteristic polynomial. So that means I want to show this equals this. So let's start off with A minus lambda I. And this is a fact that I know you know. So I'm going to say that this is equal to this. So you have to go slow through this to show all of the steps. Then I'm going to use the fact that I know A plus B transpose. You're allowed to distribute that transpose. So I'm going to say this is equal to A transpose minus, now really be careful here, you want to go slow, this transposed. Now I can say I know that lambda is just a number, so it can come outside. And I know that the I matrix transposed is just I. And I got there.